Windshield wiper motors are cheap and super strong motors that can be useful for all kinds of projects. I have put wiper motors in 2 of my robots and I found some great ways to even turn them into servo motors. But I also managed to break 4 of them, and there are so many things that I wished I had known before I started using them. In this video, I will summarize everything I think you should know about using wiper motors. I'll be visiting my friend Werner, who is an artist who works with these all the time, and we'll be talking about the specs, the different types, how to wire them, how to power them, many different ways how to drive them, how to control the speeds and how to connect to its output shafts. We'll show you how to turn them into a servo, which you can control the position of very precisely using a magnetic encoder. And I will show you all the mistakes that I made that caused me to break so many of them. The only thing that we won't do is actually putting them in a car and wiping a window. But otherwise, whether you want to build a winch or a little electronic vehicle or robots or animated sculptures or anything else that needs actuation, whether it's linear movement or rotary movement, you should keep watching, because this is everything you ever wanted to know about wiper motors. So, let's start at the beginning. What is a wiper motor? A wiper motor is a powerful DC motor with a worm drive gearbox. When the motor makes 55 revolutions, the output shaft makes only 1 turn, giving it an incredibly strong torque at a very reasonable speed. I'll demonstrate the power and give you the specs later. It's designed to go into cars and is attached to a mechanism that makes the wipers go forward and backwards. However, the output shaft of this thing will always just turn around in one direction, but it can detect by itself when the whole rotation has been made. More on that later. The motor has multiple separate windings, allowing you to get different speeds. More on that later. I'm gonna say more on that later a lot, because if I don't, I'll get completely lost, because everything about this motor is a rabbit hole that you can get lost in. Anyway, since it's made for cars, you can power it with 12 volts, but I only have a 15 volt drone battery here, but it's never given me any trouble. They're really affordable for their size. I buy them for about 30 euros new, but you can also get them second hand from a scrapyard. So, when do you think makers should consider using a wiper motor, or when should they just look at alternative options like normal DC motors or steppers or whatnot?
I think wiper motors are very handy when you don't need very precise movement.
Precise movement can be done though. More on that later.
When you need a lot of force and when you don't have a high budget. And if you just want to experiment with motors and you need a little bit of power, I think it's just really easy to go to the car scrapyard. Also really beautiful place to be, generally.
So, maybe good to know, Werner mostly uses the motors with the linkage that it is attached to in cars, which allows him to convert the rotary motion into linear motion. But maybe I should let him introduce himself.
I'm Werner. I'm an artist. I animate objects with wiper motors. I first started with one of these branches, a different one, but they look similar. And it needed a fair amount of force, and I was poor also, so I thought this would be the best solution. I'll get this one. So here you see two wiper motors. Here's one. This is a fairly old one. This is another one, and I get them off the car scrapyard. So they're about 10 to 15 euros a piece, I think. There. I can show you how it moves. This is a power supply. I use this for testing mostly, and I think this is from like DIY 3D printers or something. It's just 12 volts. Let's see if it still works. Yes. So you can also change the voltage here a little bit if the motor needs a little bit more power. Sometimes when they're really old, they need a little bit of oomph, like maybe 14 or 15 volts. Let's see. So now I'm gonna try out just half of the sculpture. So here it rotates. I can rotate it now a little bit. I can show you the other leg as well.
You just saw motors powered by a big power supply. Keep in mind that these motors can draw a lot of current and it easily peaks over 10 amps when it's powering on. And this particular one I have here settles for around 1.5 amps. So, for example, this small 12 volt supply I have here, it instantly overheats when I connect it to a motor. Make sure that you get a supply that has overcurrent protection, or the easy way to use them is to just use a battery. I use a 4-cell LiPo and Werner.
Yeah, so when I want to show my sculptures outside, I usually use these. These are just car batteries. 7 amps. They take a long time to charge, but they're really cheap. So it's 7 ampere hour, so it could supply one motor for an hour constantly on probably. And then I just connect these terminals to one of these boards probably, or this, and then you can just program that.
These boards, we have so much to cover. Oh, let's see one more sculpture and then we'll dive into all the technical details and instructions.
So this is another one of my sculptures. This is a trash can, and here I attach the motor on the outside, and it comes out on the inside here. That's actually the best way to use these motors, by just using the mechanism that was already there and using the connections points, because they're all like ball joints. So they're very stable and hard to disconnect. The other way around. Yeah, so this is also important. That sometimes the motor has a different speed depending on the polarity. So here it's quite slow. And here it's really fast. What's also good to know is that normally these motors, they have two speed settings. Often they have two windings that change the speed of the motor. So here you can see some attachment points. What I normally use for this is these ones. I use these to connect to the motor. They're called, in Dutch they're called kabelschoenen. Cable shoes. Yeah, so I connect the cable shoe with this. Crimping pliers. So normally I just test all the terminals, and then I check which ones are which modes, or which ones do something in general. Some of these terminals, they're used to control or to measure the rotations. So some just short out actually at one point. Well, maybe I can show you that. Yeah, so here, this was what we were doing, right? There are two pins on here. And when they short, the car knows it has made one rotation.
Yeah, there's normally wipers, often they go back and forth and then they stop and then they go back and forth, and that's how they...
Exactly, yeah.
Do you ever use this mechanism? Have you ever used it to measure the rotations or never?
Well, the only way I've used it, which was also nice, was that I made one rotate and then I used this shorting to control another motor. And then you really got this heartbeat effect, because it just turned on for a little bit and then it turned off, and then...
So the motor was controlling another motor?
Exactly, so
wow.
I used this shorting thing, and at this shorting point it made contact with the other motor.
But just for like a split second?
Exactly, and then it really felt like a heartbeat.
So, 5 connections, 2 for the shorts and 2 that go to different speeds.
And let's
so
see.
Usually the red is the fast one, right? And then the other one is sometimes blue, sometimes green.
Oh, they have actually more speeds. So these two? And then I can reverse them to change the speed. Of course, normally I solder these, I don't do it like this. And then I can connect this to the ground. It's very slow. And then I can connect this to the ground. It's a bit faster. And then maybe I can also reverse these. Slow. So lots of options.
You just saw that Werner could drive the motor by attaching a wire to just the metal outside of the motor, and this is one of the major pitfalls when using wiper motors. You need to understand that the ground is wired to connect to the chassis, and that means that if you have two motors in your project and you connect them in a metal frame, and then they're now electrically connected. So if you now want to reverse one motor, then you're going to cause a short circuit, which is really, really bad. Therefore, if you use more than one motor, I highly recommend to isolate the chassis from the motor. And luckily that's quite easy. You need to open it up and then remove this wire over here. This one. So that it's no longer attached to this screw which connects to the chassis. And then you can check with a multimeter to see if it's actually no longer attached. So with the multimeter I have a beep when there is continuity. And I can hold one on the chassis and hold one on the spool. And then I should get sound, because here they're still connected. But in this motor they're no longer connected, so if I hold one on the chassis and I find the ground spool, there we are. No beep, because nothing is connected. And watch out, your fingers get really greasy from working with the insides of these motors. Here I have another one where I attached a new wire, because I did eventually want to use that winding. So I soldered a wire straight to this, this new open connection, and then I ran it outside. And I also replaced, by the way, the red one to make it a little bit longer. But yeah, so you disconnect it from the ground, and then you can solder a new wire on it, so you can use it in your project. Now that you know the basics, let's shortly dive into the specs. Most of the time the reseller won't be able to disclose the basic torque specifications. They're sometimes available for more higher end motors, like from Bosch or Doka, but you pay 3 to 6 times as much for those than for the cheap ones. So I tested the torque of these, and sadly I lost the footage of this, but basically I put a hanging scale on an arm on the robot to see what kind of force the motor would stop rotating at. And I measured it to be about 25 Newton meters, which is the same as advertised for the expensive motors. A Newton meter is the amount of force that an arm can exert at a meter distance from the motor axis. So at 1 meter away it can push 25 newtons, which means you can lift about 2.5 kilograms at a meter distance of the axis. That is a lot. The RPM, rounds per minute, can differ a bit from motor to motor, and as you've seen there are even different settings on this. On these particular motors, if I can connect the high speed to the ground, then I get about 75 RPM on 15 volts, which means it should be about 60 RPM on 12 volts. Again, this matches the specifications of the more expensive motors. In theory, voltage is related linearly to speed and current is related linearly to torque. So if you block the motor and it tries to exert its maximum amount of torque, it will draw the most current, which is probably about 10 to 15 amps. I used a 10 amp motor driver when I first started, which was supposed to handle 30 amp peaks for up to 10 seconds, but it blew out immediately when I first connected it. So long story short, I don't know exactly what the upper limit is, but I can show you how to wire it so you don't have issues. More on that later. We'll get there really soon. But there are a few more things to take note of. The output shaft usually has an M8 thread with a little Conic grippy thingy. I have also seen motors with M6 threads, and there are also special shafts, but this is the most common one. To connect to it, you can either use the original wiper arm if you got it out of a car, or you can create something similar yourself by using a Conic bore. I used one that is about 30 degrees, which was hard to find and expensive, but it did work, allowing me to create an arm directly onto the screw thread. Alternatively, you can also try and extend it with a coupling nut, but of course if you spin the motor the wrong direction, it will just unscrew itself. You could perhaps weld it together, or I tried using some strong epoxy, but since you can't see if it is well applied on the threads, it may fail, and I had it happen too. I had one that didn't fail, but I then wanted to take it apart, and instead of having the epoxy break, I broke the motor instead. So yeah, at your own risk. Almost all motors will have the exact same dimensions of the motor part. Not always the exact same dimensions of the gearbox part, but always the same dimension for the mountings. It's 3 screws. I don't know what distance they are M6, but I just downloaded some random 3D model of a wiper motor and I threw them in my projects, and that has worked so far. And they're always literally the same, no matter the brand. However, there is one type of wiper motor that is very different, and that's the motor for the rear window of cars. And it has a special feature that may come in handy for you. I'll have Werner explain it.
Yeah, this is a chair I found near the trash bin.
You're telling me it's a trash chair. It looks so good.
Yeah, it looks really nice, right? Yeah, I thought it was also really beautiful. Here I used the back one. So normally cars have a different wiper motor on the front and the back. And the back one already has a mechanism which makes it just go like this instead of here where you need to attach a mechanism to make it into sort of linear motion. And I used this in an opera. This was one of the actors. It was like a dialogue with a tap dancer. To control the chair, I used a very elementary method, which was a light switch. This is the shaft of this motor is a lot longer, and then the motor is attached to this leg, and then the shaft is connected here. And it needed a little bit more force, so I helped it a little bit with another spring.
So, now we get to controlling the motor. What should you do if you don't want to use a light switch like we just saw? I use microcontrollers like Arduino or ESP32, but you still need something in between the Arduino and the motor to give it power. And there's even much simpler ways to control it so that you don't need a microcontroller at all. A relay is a little electronically controlled switch. By sending a low voltage to these two pins, the connections inside will then allow a separate circuit to close, which means to switch on. And that's where you can drive your 12 volts towards your motor. So what controls the relay? Well, Werner has some examples. How did you control your trash cans on stage?
Yeah, so because I had 13 trash cans to control, I thought it was the simplest to just use relays. So here, originally there was a peer sensor, a motion sensor, and then people walked into the space. The Arduino noticed it, and then it would send a scene, a script, to all these relays. So every relay was connected to one.
So they're just on or off, you couldn't control the direction or the speed?
Right, it's just on and off. And then here, these are two 12 volt power supplies. They need quite a lot of power actually. Sometimes these even, it was too much for them.
Do you know how much they draw?
Well, it depends. Like this one that I just showed, this is maybe 12 amps max, I think. In the start, especially when it's like starting up, then it needs a lot of power. So there was one point where all the trash cans turned on and then it would just crash.
And when it crashes, do these power supplies get destroyed or do they just stop?
No, they just stop. So it's like they have overcurrent protection. So if you just want a very simple way to just make your motor go forward and reverse, or just want to time like a motion with a pause in between without randomization or anything complex, this is a very stable way to do it. So there's a chip in here and you can basically just program the time and how many times it turns on and how much it pauses, and then it just runs infinitely if you want. It's called the IO53A02. It's an AC/DC motor reversing controller.
But these things work autonomously, they again don't need a controller or any programming?
They don't need any controller. The thing is with if you want to make something work for a long time, the more elements you put in there, the more it can break as well. So to have like a very simple controller is very nice and durable. Yeah, so if you press set, then you can change the times of the loops. Here that's 3 seconds, here it's 4 seconds pause and then 4 seconds backwards. And then I press OK, and I plug it out, and then it should work now. There's pause, backwards. And now you can also see the difference in speed when you change the polarity.
And it shows the time, no?
Yes.
Very nice.
If you want to control the motor remotely and very stably and simple, you can use these. These are remote controlled, and if you connect these to a wiper motor, you can change the direction of the motor and say when it turns on. I think it's a radio signal. You don't need a microcontroller then, no. Yeah, when I want to control the speed of the motors, I use the IBT2 motor control boards. And they have 2 chips actually to create the speed, to do the speed and direction. So here, these are the 2 chips. And you basically need to supply a pulse width modulation signal to one of these pins. And then you can determine which direction it goes in at which speed.
So yes, speed control. Let me give you a demonstration. I set up the motor here with the battery going into the motor controller, and I use an Arduino to generate a PWM signal. I like to work with Arduinos, but these signals can also be made by many radio control devices. For example, the receiver for little RC remote controllers. So the Arduino reads this potentiometer and then feeds a signal over these cables, a PWM signal into the controller, and it should look like this. I can make it go faster, or make it slow, or even reverse the direction. Like that. But can we also control the position like you can with a servo? With some modifications, yes you can. I saw a lot of people on YouTube who put some string around the shaft and wrap the string around the potentiometer, here with a little pulley for example, so that when the shaft turns, the potentiometer turns, and then you can read the potentiometer. I tried to do this in my first robot, but it's a really bad design for 3 reasons. It's hard to tighten the string, it's easy for the string to slip, and you only get a limited amount of rotation because a potentiometer can only spin like 3/4 of a circle and then it stops. So I kept on looking and came across this post on Hackaday where someone had mounted a magnetic encoder on the back shaft of a motor. So you cut open the back, I already did it here, and then you glue on this 3D printed mount, and on the back you have this encoder and you cut it open so that inside on the shaft, I don't have it here anymore, but on the shaft you would glue a little magnet. The magnet has a north and south in 2 opposite directions, and then the encoder can measure the position because it can see the rotation. And that worked great, but there's one big problem. The motor of course rotates multiple times for every revolution of the output shaft. So once it is all booted up, I can keep track of the position, but if I shut it down, I no longer know the position of the output shaft. And of course, if you need to measure the position very often, because if you spin the motor a whole round between 2 measurements, then you also lose track of the position of the output shaft. But there's an easy fix, and that is to put the magnet on the output shaft rather than on the motor shaft. So my friend Basti designed a backplate where we can mount the encoder. I have it here inside, and voila, now we have a very powerful servo. These encoders cost like €3. If you find a servo motor that can output 25 Newton meters, you will literally pay hundreds of euros, and now you can have one for about 35. Of course you need to write some code so that it can read the position, and based on that it needs to adjust the PWM signal to go towards the position. This is typically done with something called a PID loop. And motors often have different back designs, so if you want a solution you probably have to design a backplate yourself, so you need the tools and skills to be able to do this. But if you get it to work, it works great, and like this I could control position in my robot. So here I am on stage with my Acrobot. I'm exploring what it's like to perform acrobatics with a machine rather than with a human partner. And of course the legs are actuated by wiper motors. Now that you understand what's so great about these motors, let me also share one more weakness, and that is that they can break. If you repeatedly put them under high torque, or if you manage to make the output vibrate a lot when there is some load on them, the plastic gear teeth can wear down really quickly. I broke my first gear when I tried to undo some epoxy and put a lot of force on it. But my robot is designed for acrobatic performances. And whilst the Acrobot was strong enough to jump backflips, after about 15 shows it managed to destroy both the motors at the same time. On one of them the teeth wore down. Let me see this one. The teeth no longer are there. And on the other one the central gear slipped away from the shaft. It was no longer attached. So yeah, that's pretty useless. And not only does this happen when you do stunts like what I do, we also found a broken motor amongst Werner's batch of second hands. To solve this problem, I'll be using some much fancier motors for the next version of my robot. There'll be a video about this soon. But if you're not going to be constantly pushing these motors to their limits, you actually find them to be super reliable. They're designed for cars, so they're built to last for decades, to withstand a bit of rain, and to work fine even when they get a bit hot. We're almost at the end. If you've learned something new and you like this video, please consider subscribing, and if you have questions, leave them below and maybe I can help. If you want to know more about my robot, there are some videos about it on my channel, and there will be more very soon. Thank you so much for watching the whole video. It's people like you that make me want to make more, so really, thank you. And a big thanks also obviously goes of course to Werner for not only helping me with this video, but also teaching me so much in the process. So to make this video work, we cut out a lot of information and anecdotes that we recorded, but if you're interested in his work, Werner has a YouTube channel that I link in the description. Werner, do you want to say bye?
Doei.
Thank you so much, Werner. This is wonderful. And thanks for showing us in your studio.
But thank you for being here, and
thank you so much.
I hope someone has some use in the information from